you can't have any invariant metrics on these guys. Any G-invariant metric on G mod H. We've seen that this implies that you cannot map G mod H into any metric space isometrically. A property that we called metric ergodicity. It is much more powerful property than just ergodicity. For example, and this is what I spent, maybe I was boring you doing, I spent some time doing, this property, metric ergodicity, has better inheritive qualities than ergodicity itself. It passes to subgroups, it behaves nicely with lattices, etc., etc., etc. It goes to power. In the probability measure preserving, it goes to power of the space, this weakly mixing, etc., etc., etc. So this is really powerful, and the surprise is that it really happens in the nature. It's not something that I just came up with and studied the properties. It's something that happens. And it's something that we will exploit in the future. Okay? So what I want to do now, and probably I will continue next time, this is the end of this chapter, and what I wanted to do is back up to foundation of measure theory and ergodic theory, and to explain the notions I keep using. I didn't want to start with this, like a textbook, start with the preliminaries and boring you too much, but I do want to explain this. So maybe this is not the best time of the day, but this is the best time from the logic of the lectures to do it. This one. I will do now. And probably we'll continue tomorrow. And tomorrow is the last day of the week, from lecture's point of view. And next week, I will start with, I will be done with that, and I will start with algebraic group theory at the beginning of the week. And later on, I will use what we will gain from algebraic group theory and from ergodic theory and combine them up, and we will get some results. Okay, so this title now is Foundations of Measure Theory. Maybe it's too bombastic. But so I just want to clarify some notions that we keep using. So start with the notion of a Borel space. Whenever I'm using the term Borel space, this is a space with a sigma algebra. A set. Kind of space once you put a sigma algebra on it. When G acts on such a thing, Borel actions, it means that the maps are invertible and Borel. So maybe G act on X in that context means, as usual, two things. First, I'm having a map, I'm having an action map, G times X to X, which is Borel itself. So here, implicitly, I'm assuming that there is a Borel structure on G. G will be a topological group, probably in this context. Maybe nicer than that, it will be locally compact or locally compact second countable group. And this map will always be assumed to be Borel itself. A nice map in the category, the product of two Borel spaces is a Borel space. And further, this map should give an action, of course, and it should be an homomorphism into the isometries of X, the isomorphisms of X as a Borel space. Okay, this is just very general nonsense, but
Borel space does not have topology on it.
It does not have topology a priori, but of course, whenever you have a topology, then you have the Borel structure, which is the Borel sigma algebra generated by topological space, by topological sets. by open sets. If you had topological space, and if it was, I don't know, a second countable, you had a countable basis of open sets, then the Borel space that you will get will be countably generated. Countably generated means sigma algebra is generated as a sigma algebra by a countable collection, by some countable collection, which I will assume separate ones. Like, it's a metric, not a symmetric, or something like that. Or it's a T0 topological space. Example. Borel sigma algebra, the Borel sigma algebra of a second countable topological space. Another notion, countably separated. A sigma algebra is countably separated. Actually, if it contains a countably generated subalgebra, yeah, there exists a countable collection, of course, of measurable sets. Collection that separate points. So again, I said it. A Borel space is countably separated if the sigma algebra contains a countably generated sub-sigma algebra. When I say countably generated, I'm assuming the separation as well. I just don't want my words to be too lengthy. And lastly, very important, a standard Borel space, I'm defining, is a Borel space which is isomorphic as such to the Borel space coming from to a Polish space. And of course, everyone here knows what Polish space is. A separable, completely metrizable topological space. So Polish is an adjective associated with topological spaces, and this means that the topological space is separable, so it has a countable dense subset, and as a topological space, it is homeomorphic to some complete metric space. Example for such, L2 of 0, 1. Another example, 0, 1 itself. Okay? Fact, these two are Borel isomorphic. Fact, all uncountable Polish spaces are, as Borel spaces, isomorphic. Forget topologic, eh? Yes? Isomorphic. It's quite surprising if you see it for the first time, but it's not hard to establish. I will not prove this one. I will maybe discuss an analog, a slightly weaker analog of that. But that fact actually gives this power of this nice definition here. Of course, I can discuss the space with 1 point or 2 or countably many, but if you ignore these guys, all spaces you know from geometry and analysis are basically the same. Or not all spaces. L infinity of 0, 1 with the norm topology is not. It's not the same, but mostly once they are separable, they are nice enough, they are the same space. Of course, the group actions on that same space could be very different. But as a space, it is all the same space, and this is what we call the standard Borel space, or a standard Borel space. This is an isomorphism class. And of course, so standard implies, I guess by this remark here, finitely generated, which implies finitely separated. Countable. Thanks. Okay, so much about Borel spaces, but I'm not really interested in Borel spaces. Oh, I am, but I'm interested in two kinds of spaces. In Lebesgue space again, I have two sides in my mind: Lebesgue, Borel. Borel are the targets of arrows, and Lebesgue is the actual spaces I'm living in, and this is a Borel space with some extra structure. So maybe I should start by the following. Do you want to leave now or to spend 5 more minutes?
5 minutes, okay.
5 minutes, okay. Let me not define what the Lebesgue space is, but give you a theorem. Every countable generated Borel space with an atomless measure or measure class is Borel or Lebesgue isomorphic. So this is the Borel isomorphic, but I'm allowing myself to forget the null set. To 0, 1, seek Lebesgue. Let me sketch this, and this will be the starting point of our discussion tomorrow. So this is some sort of, in a sense, this is a weaker version of that one. But something which is very easy for me to describe. I will do it, I will sketch this. I will take 3 steps. X, my unknown guy, is isomorphic to a Cantor set plus some unknown measure. And let me sketch this, it's very easy. So I'm having X, in it I'm having the collection AN that countably generate my space, and I will define the map from X to 0, 1 to the N by sending X to, well, this is a Cantor set, right? And this should be a sequence. And the sequence is 0 or 1s according to whether I am in AN or not. Chi A N X, this will be my N. And okay, you should check whether this is indeed an isomorphism. So the fact that this is an injection is the separation of points by AN. It is measurable by the fact that the ANs are measurable, etc., etc., etc. In order to invert the map, I have to ignore some null set here, because maybe I'm not on. So the fact that this is an isomorphism means, for me, this is not Borel isomorphism. This is a big isomorphism. Okay? I'm only sketching.
But if you ignore this null set, you still have counter set, right?
Yes. Correct. Step 2, X is iso to 0, 1 plus some measure. This is also very easy to do because, well, I can just take a standard embedding of the counter set into 0, 1, which you show your students by rising points to them. Binary embedding. And step 3, so what do I get? Up to now, my unknown space became a very familiar space, the unit interval with an unknown measure. But now just to standardize the measure on 0, 1 itself is something which is very easy to do. Take a map from 0, 1 to 0, 1, which takes the point T to the measure up to T. So it's make everything straight. And here I'm using the fact that there are no atoms, and now you must ignore null set if you want to invert it as well. But
the measure was probability.
also, okay, somehow I didn't define a measure class. In the measure class, when I'm saying a measure class, I'm always assuming it's the class of some sigma finite measure, which can always be assumed to be probability. Actually, I will be, as I was more precise about the Borel structure here, this is just a preparation, I will be more precise tomorrow about Lebesgue spaces, and I will be formal in the definition. But this is just a preparation. Okay, so by these 3 steps, once properly proven, which I didn't do, but I don't care now that much about the proof that's here. This is enough for me. Basically, one sees that as there is a unique Borel space, there is essentially a unique Lebesgue space. And we will discuss this tomorrow again. Okay, I'm done.
So do you claim that there are Borel spaces that do not support multi-class?
Of full support?
I'm just trying to understand this theory. Yeah, of full support.
Let me say that there are measures which are not equivalent to any probability measure. Take uncountable set and the counting measure on it. I mean, weird thing may happen. I will touch those things tomorrow, but take L infinity of 0, 1, space of all bounded measurable functions of 0, 1, and observe that this is a C-star algebra. Okay? So it commutative 1. So it has a spectrum. So there is some compact topological space, very weird, such that the continuous function on it are in one-to-one correspondence with measurable functions on 0, 1, the interval, up to 9 sets. And there is a canonical measure class on this space. But this is something very weird. Okay, so weird thing may happen if you don't assume some probability or some standardness of things. how much the theory of C-star algebra, so the basics or anything, von Neumann algebra is known? Yeah.
Not much.
Not much.
That's the measures.
I mean, the theorem by Gelfand that there is a spectrum to a commutative C-star algebra, which is a compact topological space. Is this known? Okay. I will not really use this, but maybe I will remind you.